Welcome to the lesson Introduction to Regression, in which we will discuss the regression model member in the family of machine learning supervised algorithms. The objectives of this module are to discuss the goals of regression, describe ordinary least squares, define how to measure performance for regression, and to describe the balance between bias and variance in regression. In this section, we'll discuss the goals of regression. Recall we have two families of machine learning algorithms, supervised learning, which uses labeled target values, and unsupervised learning, which does not use labeled target values. Regression is a supervised learning algorithm, so we will use regression to predict a target or label based on the inputs x1 to xp. For example, suppose we have collected and recorded the weight and height of many individuals, and we wish to predict the weight based on the height. One way to do this is to try to find a line that fits the data. We can draw such a line and represent it using the familiar y equals mx plus b notation, where y in this case is the weight we're trying to predict, and x in this case is the height. The value m represents the slope of the line, and the value b represents the y-intercept when x equals 0. In this example, we're using one independent variable, height, to predict the dependent variable, weight. When we do our hands-on exercises, we're going to be predicting a dependent variable, one of those phenotypes like intraocular pressure or microscopy values, from the retina gene expression values, the independent variables, which in that case number in the thousands of genes. There's a way to quantify how well the line we plot fits the data we're given. In this slide, we have 10 points xi, yi, and we've plotted a line using the formula y equals mx plus c. Some mathematicians use c instead of b to represent the y-intercept for some reason. To quantify the goodness of fit, we add up all the squared differences of the actual yi values from the line we plotted. We square the difference, also known as the residual, because some differences are positive and some are negative. The objective of the linear regression algorithm is to minimize the sum of that squared distance. The previous slide showed only one independent variable as a predictor of y, but in practice, we will have many independent variables. This slide shows the general form of the linear model we're trying to build, where each value y hat, designating an approximation of the value for y, is predicted using a linear model, w naught, the intercept term, plus weight 1 w1 times input x1, plus weight w2 times input x2, plus dot, 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 all the way up to weight wp times the input xp. In this section, we describe the method of ordinary least squares as an algorithm to fit the best regression line through a set of given points. Ordinary least squares, or OLS, squares the difference between the actual value y and the predicted value y for each point P1 to P6 in this slide. The red squares represent the fact that we are squaring the differences. We sum up the squares to get the sum of squares, in this case 0.51. The equation of the line of best fit in this case is given as y equals 0.40x plus 0.51. So the slope is 0.4 and the y-intercept is 0.51. The algebraic representation of OLS is shown in this slide. Don't fret the mathematical notation, it's super easy. In order to find a linear model y equals mx plus b, we need to find the slope m and the y-intercept b. These equations show us how to do exactly that. The slope m is given by the top formula, and the y-intercept is given by the bottom formula. Let's unpack the top formula for slope. X bar is the mean of the x values, so you just add them all up and divide by the number of values. Y bar is the mean or average of the y values, so you just add all those up and divide by how many there are. Xi minus x bar is the difference in the ith x value and the mean of x. And y minus y bar is the difference between the ith value of y and the mean of y. Take the product of those differences and add them all up, and that gives you the numerator for the slope m. The denominator of the slope m is the sum of squares of the differences between each value xi and the mean value x bar. Once you calculate m, you can calculate b as the difference between the mean value y bar and the product of m and the mean value x bar. We call this a closed form solution, meaning we can calculate exactly the values of m and b rather than approximate them. All you have to do is roll up your sleeves and do the arithmetic. Of course, we're data scientists, so we'll want to automate this using software. In the next slide, we'll see an example of using OLS to draw a line. So this is a handwritten example on the left where I have a number of points in a table, and on the right, you can see the points that I've plotted. So you can see there's 10 points there. For example, there's the point 1, 1, there's the point 1, 2, there's the point 2, 1, the point 2, 2. All these dots here represent points in the data set, and we wish to fit a regression line through that, which I've already done here. But I got that line by doing the arithmetic on the left. So I've laid out all the points x and y, so 1, 1, 1, 2, 2, 1, 2, 2, etc. And then I calculate the difference between x and x bar. So x bar is the mean value of x. So I just add up all the x values in the x column, divide by 10, I get 3.9. Same for y bar, I just add up all the values in the y column and divide by 10, and that gives me y bar. And then the x minus x bar column is x minus x bar, so 1 minus 3.9, which is negative 2.9. And so on down the line. I calculate all the x minus x bars, I calculate all the y minus y bars, and I calculate x minus x bar squared in the 1, 2, 3, 4, 5th column. And in the last column, it's a little hard to see, but that's the product of x minus x bar times y minus y bar. And so you can see, for example, negative 2.9 times negative 1.7 is 4.93 in the last column. Now, if at the bottom of those columns, I sum them up. So the sum of x minus x bar squared is 36.11. The sum of the product x minus x bar times y minus y bar is 13.45. So now I have all the information I need to plug into the equation from the previous slide to calculate m. So I just plug those numbers in for m. The sum of x minus x bar times y minus y bar is 13.45, and then I divide by the sum of x minus x bar squared, which is 36.11, and I get approximately 0.37 as the slope. Now, with the slope, I can plug that into the second formula for b, which is y bar minus mx bar. And I know what y bar is, I know what m is, and I know what x bar is. Plug those in, and I get 1.257. Now I have my m, I have my b, and I can now I have my form y equals mx plus b. In this case is y equals 0.37x plus 1.257. And that's the line that I plotted on the right. And you can see that does a pretty good job of fitting that data. Now, there's a term called homoscedasticity and heteroscedasticity, which describe how much the data varies as the size of the data changes. So as we go from left to right, for example, for the homoscedasticity plot, you can see that the variance, or how much the data varies between the data points, doesn't vary very much. On the right, however, as we move from left to right, the data get more scattered, and that is called an effect called heteroscedasticity. And the method of least squares that we're using here is vulnerable to heteroscedasticity. We're not going to talk about it much more. I wanted you to be aware of it. And in the hands-on exercise, I'll show you a way that you can use to identify whether there is heteroscedasticity in the data set. So in this section, we'll describe how to measure performance of regression models. One measure of performance is called mean absolute error, and it's exactly what it sounds like. It's the average or mean of the absolute values of the differences between the actual value y's, yi, and the model predicted y's, y hat. The vertical bars denote absolute value. The Greek letter sigma denotes sum, and in this case, we're summing from I equal 1 to I equal n. And 1 over n denotes the fact that we're finding the mean or average of these values. Mean squared error is another metric for measuring the performance of regression, and it's exactly what it sounds like. It's the average or mean of the squares of the differences between the actual values yi and the model predicted values y hat, or in this case, it looks like it's a tilde. Again, the Greek letter sigma denotes the sum, and 1 over n again denotes the fact that we're finding the mean or average. So the mean squared error has the effect of amplifying outlier error terms because numbers greater than 1, a square is always greater than its absolute value. The value of MSE or MAE for that matter, are sort of meaningless unto itself. What you need to use, the way you use this is to compare one model from another when you're selecting the best model. R squared is another term. It's also called the coefficient of determination. And it's another metric used to quantify the performance of a regression algorithm. And what it does is it determines the proportion of the variance in the dependent variable that can be explained by the independent variable. In other words, R squared shows how well the data fit the regression model. It's also called the goodness of fit. R squared is probably a better metric of performance than mean average error or mean squared error when comparing two different models on two different data sets. The formula for R squared is given in the slide as 1 minus the ratio of the sum of the squares of the residuals to the total sum of squares. The latter term ranges between 0 and 1, so the difference 1 minus that term ranges between 0 and 1 as well. The closer to 1, the better the fit. The closer to 0, the worse the fit. As we will see in our hands-on lab, a very high R squared value simply means the line is very good fit for the given data points, but it doesn't mean the regression model will perform well on out-of-distribution data. In this section, we discuss the concept of bias and variance and how to balance them in regression modeling. Bias and variance are terms used in statistics to capture prediction error and model variation. This slide shows a set of 4 targets to portray high and low bias and variance. Take the first target on the left. The dots in the target, probably formed by someone throwing darts at a dartboard, for example, are tightly clustered in the first ring away from the bullseye. This dart throw is very precise. In other words, the darts were consistently thrown very close to each other, but not very accurate. The darts were not that close to the bullseye. The consistency of the throws is captured by the variance term, and there isn't much variance between the dart throws. The error of the dart throws, how far away it is from the bullseye, is captured by the bias term, and there's high bias in all those dart throws. If you look at the third target from the left, all the dots are surrounding the bullseye. This indicates that the dart thrower was accurate, but the dots are scattered all around the bullseye. This indicates that the dart thrower wasn't very consistent. A model which predicts as such is said to have low bias and high variance. Take a minute to talk yourself through the other 2 targets. Low variance and low bias is the second from the left, and high variance, high bias is the one on the far right. So we've seen that some models are better than others. In the previous slide, we discussed bias and variance as descriptors of a dart thrower. Now we discuss how bias and variance contribute to the goodness of a model. Looking at the slide, we see 3 different models in red, all designed to capture the trend of the data points in blue. It's sort of like the Goldilocks of regression models. The model on the left is an extreme version of trying to capture exactly the distribution of the data points. It has no flexibility, but it's extremely accurate. The problem with this model is that while it fits the training data very well, it will not likely perform well on data it has not seen before. We say that such a model with high variance and low bias does not generalize well to out-of-distribution data. The model in the middle is the opposite of that. It's very flexible, but it's not very accurate. The problem with this model is that even though it's very general and flexible, it doesn't fit the training data well, nor should we expect it to perform well on data it hasn't seen before. We say that this model too, with low variance and high bias, also does not generalize well to out-of-distribution data. The model on the right is just right. It balances um, some bias and some variance in the model, but not too much of either one so as to not overfit or underfit. So in the previous slide, we used our eyes to judge whether a regression model was underfit, overfit, or just right. But when we build models using software and we wish to automate that, and since our software doesn't have eyes, we need to capture that in some sort of metric or number. This slide suggests that the number and calls it cost. The cost is typically represented by the error in the model, the term on the left called loss, and the algorithms we use to try to minimize that error when building models. One way for us to prevent the algorithm from overfitting the data is to introduce a term called a regularization term. This term is the sum of squares of all the weights. The more weights the model uses for regression, the more overfit the model is to the data. So by adding this term to the cost for the algorithm to minimize, we're forcing the algorithm to take into account how complex the model is. The more complex the model, the more overfit it is. The more overfit it is, the higher the regularization term. The higher the regularization term, the higher the cost. The lambda coefficient in front of the regularization term is a hyperparameter for us to configure when using regularization. And it dictates how much we want to penalize the model complexity. This value ranges from 0, which is no regularization, to an arbitrarily large number, which is maximal regularization. And that brings us to the end of this lecture in which we discussed various concepts of regression modeling from the supervised family of machine learning algorithms. In the hands-on activity, we'll have the opportunity to use the algorithms and tools we learned in this lesson. Specifically, you'll use linear regression to predict phenotypic responses from gene expression data using plain old linear regression as well as regularized regression. As a bonus, you'll also evaluate the gene expression feature space for heteroscedasticity.